we have an exponential equation that has a floor or a ceiling function as its exponent. And let's just work with the constant that's given, although that's not particularly well motivated at this point. Now I'm going to write down the ceiling. Now, y'all, the ceiling is sometimes called the least integer function, not the greatest integer function, because it returns the least integer that's greater than the input argument. A little bit of a mouthful. But let's write down the ceiling of this number that's between 0 and 1, 144 over 625. You guys already know this is the quotient of two square integers. So we got 625 here. Now again, the ceiling function, if you take a look at this definition, notice that would be between c minus 1, which would be 0, and 1, right? And so 1 is the ceiling, so this would actually be equal to 1. Now notice that gives us a very quick answer right down here. When x is between 0 and 1, okay, the right-hand side of the equation happens to be the answer because its ceiling is 1 and you get x to the 1, right? So x equals, I'll just write it up here, x equals, and I should say solve up here, okay? We're trying to solve this equation, okay? So by inspection almost, if you're familiar with the ceiling function, x is equal to 144 because it's effectively just the identity function in that particular interval, all the numbers between 0 and 1. So x equals 144 over 165 is what a lot of people would call trivial, that condescending sounding term, solution. Okay. Now, so are there any others? Well, one way to look at this function, notice that the one right above here, if x is between 1 and 2, you're already squaring, and you're going to get when you're squaring a number between 1 and 2, you can't possibly get this number, right? So you don't have to worry about going any higher now, but how about to the left? Well, on the interval from 0 to, or minus 1 to 0, the ceiling is actually 0, right? 0 is the largest integer for any number between minus 1 and 0, all right? And so x to the 0 is equal to 1, all right? Well, 1's not equal to this number, so we can move on to the next one. Now, y'all notice what happens here when you're in negative intervals. When you're in negative intervals, by the property of exponents, you get a reciprocal condition, okay? 1 over x for all numbers between minus 2 and minus 1. And then notice here we get this condition that looks favorable, and let me point out why. Notice that this is equal to 12 squared. And I did that you don't have to do this, it just makes the computations a little bit easier, I suppose. But it is the quotient of two square integers. I refuse to call them perfect squares. Okay, so 12 squared is 144 and 25 squared is 625, all right? Now notice what happens down here. If you're in this region, the only number that would work, the reciprocal you invert, the only number that would actually work here, and this is by inspection, hopefully you think this is fair enough. If you choose x equal to, you need two conditions. You need this squaring condition, it appears, or maybe, you need the squaring condition, it appears. But also you need a number that will give you minus 2, so you'll have 1 over x squared. So you see what you have right here is x is equal to minus 25 over 12. Minus 25 divided by 12. And y'all, you see that's the negative reciprocal of what we had up here. Well, almost, you gotta square it to get this right and then invert it, right? But anyway, you can see that this works if you substitute in here. The minus sign goes away. You get 625 over 144, but that when you invert it, when you get its reciprocal, you'll get the statement up here, okay? So now, and I'll go ahead and wave my hands that once you start getting like 1 over x cubed, the numbers are getting closer and closer to 0. As this exponent gets bigger and bigger, I stopped at 4 arbitrarily, but you can see you're getting numbers that are super small, very, very small, much smaller than an already small number, which is 144 over 625. Again, not a formal proof, but as far as I know, these are the only two solutions, I will stand by it. I'm pretty sure that these are the only two. Again, I'm not rigorously trying to prove it, but hopefully it's fairly convincing. You know, there's not going to be any solutions to the right. You know, once you get up to x cubed, x to the fourth. You know, here it can't be because it's just equal to the constant of 1. It doesn't work here, and you can. It's not hard to check this really. Okay. So again, these are the two solutions I got, minus 25 over 12 and 144 over 65. Okay, let me know what you thought. It's kind of fun. It's kind of a fun problem. There's a lot of stuff you could do with this problem in a piecewise fashion, you know, challenge type problems you might want to do. When does it equal a linear function, a quadratic function, square root functions? I'm not sure I would work out with logarithm functions. That might be tougher, but you could, I set it equal to a constant just as a warm-up video. But you can set it equal to like square root of x, for example. How would you work that problem? Or remember, this function grows so fast, square root function, it may not have a solution, you know. So, well, I guess it would have to on a linear piece, wouldn't it? Yes, yeah. Probably, yeah, it would probably be something trivial, you know, in the interval 0 to 1. But in any event, that does it, folks. Thank you for viewing.